Namaste and welcome back to yet another lecture on linear algebra through geometry. In the last lecture we looked at the idea of distance from a point to the plane passing through the origin and orthogonal to another vector, and we also looked at distance from a point to the line joining to the line passing through another vector, let us say u. This is what we had looked at, and the very basic idea of looking at all these things is to find out is there a way in which we can get the area of a parallelogram formed by two vectors in 3 dimension. So, suppose I have two vectors, let us say u and v. I want to figure out what is the area of the parallelogram, that is for which the vectors u and v form the adjacent sides of the parallelogram or the sides of the parallelogram. So, I want to figure out what is the area of it. This is exactly what we did in 2 dimension also. We found out that the area of the parallelogram which is formed by, let us say, two component vectors was actually the determinant of the matrix in which these two vectors were actually the columns of the matrix. We figured out that the area of the parallelogram, recall, let us do this. So, recall if let us say u was a vector, say u1 u2 and v be the other vector, okay. If we were two vectors, say such that two vectors such that let us say the matrix A is defined as A is equal to this vector u and the vector v. We are going to put this, that means the matrix A is going to be, the matrix A is going to have these vectors as the columns u1 u2 v1 v2. We figured out that the determinant of this matrix A, determinant of A, which is u1 v2 minus u2 v1, was actually the area of the parallelogram, area of the parallelogram formed by these two vectors. So, suppose we have this, let us say we have this vector u and we have this vector v, and we said that okay, this is going to be vector v and that is going to be vector u, that is going to be the vector u. We said that this area of this parallelogram is basically given by the determinant of this matrix. This was all fine in 2 dimension. Now, we want to look at the same thing in 3D. Suppose I have this vector, say suppose let u be equal to this u1 u2 u3 and v another vector, let us say v1 v2 v3. Yeah. Now, these are, let us say, two vectors. So, I have my 3 axes, let us say the E1 axis, E2 axis and E3 axis. Suppose I have this, let us say this is going to be my vector u, and let me take this to be my vector v. Basically these two define a plane, and we see that okay, we actually get into we get a parallelogram here. Now, I want to find out what is the area of this parallelogram. The only thing is this vector u is going to be a 3 component vector here, and v is another 3 component vector here, and if you have a matrix A and then you put these as the, let us say, the 2 rows of the matrix, let us say u1 u2 u3 V1, V2, V3, there is no way we can find the determinant, because determinant for this matrix is not even defined. So, how are we going to find out the area of this parallelogram? That is the question that we are going to ask, right. So, we are going to look at how do we find the area of this parallelogram. So, for that what we do is we use the idea of finding the length of finding the distance from a point x to the line which is passing through another vector v. So, that is exactly what we did in the last class, and that is where we are going to move forward with. Okay, so let us do this. Recall. We said that the distance from a point x to the line along a non-zero vector u along u not equal to 0, it is not the 0 vector. Basically we figured out that this was given by the projection of the length of this. So, let us look at this again geometrically, we will be able to understand. So, we had this, let us say we had this vector x and we had this vector which is say u. Now, we said that we wanted to find out this is basically the line passing through the origin and along the direction of u. This is, let me call that as line L. Now, what I want to find out was I wanted to find out the distance from this point x to this line which is passing through the origin and in the direction of v. This is what I want to find out. This is nothing but if suppose we have this to be the projection of this vector x along the direction of u, and this is the vector x, this is nothing but the vector which is x minus the projection of this vector x along the direction of u, and this is precisely the length of this difference vector is precisely the distance from the point x to the line passing through the origin and in the direction of u. So, that is exactly what it is, and we figured out that this was given by, so we said that x, the length of this x minus basically the difference vector x minus p of x, the length of this was given by square root of x dot x into u dot u minus x dot u the whole square divided by the length of this vector u. This is what we had. Now, how are we going to use this fact in our efforts to find out the area of the parallelogram which is formed by two vectors in 3 dimension. So, that is what we are going to look at, right. So, let us take this. Let us say I have this, my axis is all done. Now, what I am going to do is I am going to take two vectors, namely the vector u and v. So, let us take this to be my vector u, and let us take another vector. This is basically, let me take this as the vector v. Now, we can complete the parallelogram here. So, this is going to be the vector u again, and that is going to be the vector v, this is the vector v. Now, I want to find the area of this parallelogram is basically given by area of the parallelogram is given by base into height, which we all know. The height is basically here, this is the height that we are looking for, and that is exactly the length of the difference vector. What is the difference vector here? I want to look at the the difference between the vector u and the projection of this vector u along the direction of v. So that is going to be my height. This height vector, the height is going to be the length of this vector, which is u minus projection of u in the direction of v, right. So the area of the parallelogram is given by, and area is given by b into h, where base corresponds to the length of the vector v. The vector v is there, so the length of the vector v is the base, right. This is what we have. And what is the height? The height is precisely this, replacing x with replacing x with u and u with v, we are going to get this. So the height is going to be the vector u minus the projection of the vector u along the direction of v, which is given by square root of u dot u into v dot v minus u dot v the whole square divided by the vector length of v. This is exactly what we have. Therefore, the area is given by, area is base into height, which is nothing but square root which is nothing but 1 by the length of v into square root of the base into height this is nothing but the length of v into square root of height is nothing but u dot u into v dot v minus u dot v the whole square divided by the vector length of v. These two get knocked off, therefore, what we get is area of the parallelogram. So, area of the parallelogram is given by is equal to square root of u dot u into v dot v minus we have u dot v the whole square. That is the area of the parallelogram. Is that okay? Now, we are going to look at something very interesting from here. Another way to interpret this, just do a little bit more, we just walk the extra mile here. We are going to figure out something interesting. What is u dot u? This is nothing but square root of u dot u is nothing but the squared length of the vector u and the squared length of the vector v minus u dot v the whole square. Recall, this is nothing but u dot v the whole square. Now, we know that u dot v is nothing but the magnitude of the vector u, the magnitude of the vector v into cos theta. So, we are going to plug that here into this equation, let us say 1. So, we are going to get area is equal to square root of length of u squared, squared length of v minus we have this, which is nothing but again u into v into cos theta the whole square, which turns out to be u v square root of 1 minus cos square theta. So, you get sin theta. So, this is the area that we are going to get, right. Now, this is the area of the parallelogram that we have, uv sin theta, which means there is a problem here because your sin theta can be negative also. That means that negative sign is going to talk about the orientation of the parallelogram. So, that is how you are going to take it. What we do is we will also try to interpret this area of the parallelogram through something else, which we are going to do right now. We are going to look at it from the system of equations perspective, and then we are going to look at finding out the area of the parallelogram again through the system of equations. So, what are we going to do? Let us look at this. Consider the following system of equations. Consider, I am going to have these two equations, which I am going to say it as u1 x1 plus u2 x2 plus u3 x3 is equal to 0, v1 x1 plus v2 x2 plus v3 x3 is equal to 0. So, I want to find out the solution to the system of equations. So, the idea is to find the solution to the homogeneous system of equation to the above system of equations, right. That means we want to find out the values of x1, x2, x3 such that you can you get the value of x1, x2, x3, which basically satisfies this set of equations. So, suppose if I want to capture this in terms of matrix, which we did in the previous lectures, where we had Ax equal to 0, the same format I can actually capture this system of equations in terms of matrix. So, where I am going to write this matrix as, let us say, u1, u2, u3, v1, v2, v3 into x1, x2, x3 is equal to 0, 0. This is what we are going to have. Now, if you look at the two equations, if you look at these two equations, it is something interesting which we observe. What is that we observe? We see that u1 x1 plus u2 x2 plus u3 x3 is equal to 0 is of the form u transpose x is equal to 0, which is of the form u dot x is equal to 0, where the vector u is basically u1, u2, u3. Similarly, we have v1 x1 plus v2 x2 plus v3 x3 is equal to 0, which implies we have v transpose x is equal to 0, which implies v dot x is equal to 0, right. We see v dot x is equal to 0. Now, what is interesting is you want, if we reinterpret this equation as u dot x is equal to 0 and v dot x is equal to 0, this simply means we are trying to find out a vector x which is orthogonal to both the vectors u and v. So, this implies find that vector x, find the vector x which is given by x1, x2, x3 orthogonal to both u and v, orthogonal to both u and v. Now, how do we find this? So, we will take the help of our system of equations again. We had u1 x1 plus u2 x2 plus u3 x3 is equal to 0, v1 x1 plus v2 x2 plus v3 x3 is equal to 0. Now, what are we going to do? Let us call this as equation 1 and let us call this as equation 2. What am I going to do? I am going to multiply equation 1 by v1 and equation 2 by v2, equation 2 by v2. I am going to subtract So, I am going to multiply equation 1 by V1 and equation 2 by V2 and subtract the second equation from the first one. So, I am going to do this. So, if that is the case, then what I will get? I will get U1 V1 x1 plus U2 V1 x2 plus U3 V1 x3 is equal to 0, and I am going to get U1 V1 x1 plus V2 U1 x1 plus V3 U1 x3, this is x2, x3 is equal to 0. If I subtract, I am going to get this knocked off. So, I am going to have x2 into V1 U2 minus V2 U1 plus x3 into V1 U3 minus V3 U1 is equal to 0, right. I am going to get this. Similarly, I can do the, so this is, let me call this equation 3. Similarly, I can do the following. Similarly, we can multiply equation 1 by V2 and subtract the second equation multiplied by U2. So, what do we get? We get U1 V2 x1 plus U2 V2 x2 plus U3 V2 x3 is equal to 0, and I am going to get, excuse me, V1 U2 x1 plus V2 U2 x2 plus V3 U3 V3 U2 x3 V3 U2 x3 is equal to 0. Now, if I subtract, this gets knocked off. So, what do I get? I get x1 into U1 V2 minus U2 V1 plus x3 into U3 V2 minus U2 V3 is equal to 0. This is what we get, right. Now, you can see that there are again pairs of equations. So, I can write, I can easily figure out what is the value of x1 and what is the value of x2 that satisfies this equation. So, we will see that if you take the negative of this and then put here and then you multiply for x3, you give this value which is U1 V2 minus U2 V1, you will end up getting this to be 0. So, what are we going to do? We are going to do the same thing here. So, choosing x1 is equal to U2 V3 minus U3 V2 x2 is equal to U3 V1 minus U1 V3 and x3 is equal to U1 V2 minus U2 V1. We basically get if we substitute these values in the original equation, we get A dot x is equal to 0, we get Ax is equal to 0, right. Now, what is interesting is the solution vector, the solution that we have, x is basically equal to U2 V3 minus U3 V2 U3 V1 minus U1 V3 U1 V2 minus u2 v1 is basically what we call as the cross product. We define this as the cross product of u and the vector v, right. We define this as the cross product of u and vector v. So, let us write that again. So, if u is this vector u1 u2 u3 and v is this vector v1 v2 v3, we define the cross product as cross product of u and v as u cross v is nothing but u2 v3 minus u3 v2 u3 v1 minus u1 v3 u1 v2 minus u2 v1, right. This is how we define as the cross product. If you look at this, the cross product is actually given as a vector. So, we are going to define the cross product as that vector, and this vector whatever that we got as u cross v is orthogonal to both u and v. So, the cross product u cross v as this, that as the vector, which is perpendicular to both u and v, which is perpendicular to both u and v. Is that okay? So, that is the cross product that we are going to define. Now, where do we go from here? Let us keep this in mind, let us have this particular expression in mind. What are we going to do? We are going to go back to the case where we found out the area of the parallelogram. We had this area of the parallelogram which is spanned by basically the vector formed by the vectors u and v, right. We said that the area is equal to square root of u dot u into v dot v minus, we said that u dot v the whole square. This was what the area of the parallelogram was. So, what are we going to do? We are going to substitute all these values and see if it actually if you are able to if you are able to combine whatever that you have studied in terms of system of equations and in terms of the vectors, right. So, let us do this. So, what is this? U dot u is nothing but square root of u1 square plus u2 square plus u3 square, right. Is that right? Square root of u1 square plus u2 square plus u3 square, but this is u dot u. U dot u is basically, okay, let us do this. Let us take this. This is so u1 square plus u2 square plus u3 square into v1 square plus v2 square plus v3 square minus u1 v1 plus u2 v2 plus u3 v3 the whole square. This is what we are going to get, right. If you do this, we find something interesting. So, if we simplify all these things, let us expand the bracket and then do all the kind of simplification. Let us do this. So, what are we going to get? We are going to get u1 square v1 square plus u1 square v2 square plus u1 square v3 square plus u2 square v1 square plus u2 square v2 square plus u2 square v3 square plus, okay, I will put all these things together, plus u3 square v1 square plus u3 square v2 square plus u3 square v3 square minus, we are going to get the same thing u1 v1. So, you are going to get u1 square v1 square minus u2 square v2 square minus u3 square v3 square minus 2 u1 v1 u2 v2, is that right, AB. So, u2 v2 minus 2 u1 v1 u3 v3 minus 2 u2 v2 u3 v3. So, this is what you are going to get. And if you see here, all these terms get knocked off, this gets knocked off, this is knocked off, u2 square v2 square, u2 square v2 square get knocked off, u3 square v3 square get knocked off. So, what are we going to get? We are going to get this u1 square v2 square plus u1 square v3 square plus u2 square v1 square plus u2 square v3 square plus u3 square v1 square plus, okay, u3 square v2 square minus 2 u1 v1 u2 v2 minus 2 u1 v1 u3 v3 minus 2 u2 v2 u3 v3. Now, this is of the form, if you again try to simplify this, this is precisely what you will get. We have this u1 square v1 square, u1 square v2 square, and then u2 square v1 square. So, you have u1 v2 minus u2 v1 the whole square, right. We will mark all those terms. So, this is one, this one, this one and this one, that gives me u1 v2 minus u2 v1 square the whole square plus, if you look at the next one, it is u1 v3 and u3 v1. So, I have u1 v3 minus u3 v1 the whole square, which is basically this guy u1 v3 my u3 v1 and this fellow plus, okay, plus what do we have? We have u2 v3 minus u3 v2 the whole square, which is basically this guy, right, this and that. So, what are we going to get? Let us rewrite this. So, this is going to be u2 v3 minus u3 v2 the whole square plus u1 v3 minus u3 v1 the whole square plus u1 v2 minus u2 v1 the whole square. What is this? This is exactly the length of this vector u cross v, u2 v3 minus u3 v2. So, you had this u2 v3 minus u3 v2, then we had u3 v1 minus u1 v3, u3 v1 minus u1 v3, that is exactly what you have here. You can of course, since it is in square, so you can actually, okay, we will rewrite this, we will just make it this way u3 v1 minus u1 v3. So, we will write this as u3 v1 minus u1 V3 the whole square plus that. So, what we have here is the area of the parallelogram is basically the length of the vector which is u cross v, which is basically the norm of this vector. What is that vector? u2 v3 minus u3 v2, u3 v1 minus u1 v3, u1 v2 minus u2 v1. That is the area of the parallelogram. So, that is very interesting that if you look at a parallelogram formed by two vectors in 3 dimension, the area of the parallelogram corresponds to the length of the vector which is orthogonal to both. That means, the area of the parallelogram formed by the two vectors u and v in 3D it corresponds to the magnitude of the cross product of the two vectors. That is the most interesting stuff. And what we do is we will stop with this, and in the next class when we in the next lecture what we do is we are going to look at something more interesting, like how does this come to this. In fact, if you look at every element of this cross product, it looks like the determinant of a 2 by 2 matrix, and that is exactly what we are going to focus in the next class. We are going to look at this area of the parallelogram that is formed by two vectors in 3 dimension in terms of parallelograms. I mean, in terms of as we see, the components are all determinants. The components being determinant tell that okay, you are going to have parallelograms in 2 dimensions. So, how are we going to connect these two ideas, and that is exactly what we are going to see in the next class. In the next lecture we will also be looking at the idea of volume, because we are going to add one more vector to it. We are going to look at the volume of a parallelepiped, and we are going to look at the properties of the cross product and lot more. So, in the next class, so the question that we are going to have, the cross product u cross v has elements, has components which resemble that look like the determinant of a 2 cross 2 matrix, the determinant of 2 by 2 matrices. So, how do we interpret this? So, the question is, how do we interpret this? The second question that we are going to answer in the next lecture is basically, okay, we have two vectors which are on which are what do you call, let us say linearly independent in this case, where the area is going to be finite. I mean, it is not 0. So, what we are going to say is, suppose I have another vector, a vector w. Suppose we have u, v and w, 3 linearly independent vectors. U, v, w are 3 linearly independent vectors in 3D. Now, what is the geometry formed? What is the geometry formed? And what are the features? So, that is exactly where we are going to get to the idea of volume of a parallelepiped and so on. So, in the next lecture we will answer these two questions. In fact, there is something very interesting, a different form of Pythagoras theorem that comes into picture here. So, that is what we are going to look at in the next lecture. Thank you.